Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
Hey everyone, excited to dive into another fascinating paper today. I've been looking forward to this one.
Yeah, I'm curious to see what we'll make of this, I admit. The title itself is a bit provocative, right? Are language models actually useful for time series forecasting?
It definitely is. It's something we've touched on before, how language models are being used in all sorts of areas. But it's good to have some concrete analysis. Trying to bridge that gap between understanding language and predicting time series data feels like a bold move.
Exactly. And it makes sense in a way, right? Time series, like language, has these sequential dependencies, these patterns over time. So, intuitively, you'd think a language model, which excels at capturing these dependencies, would be good at forecasting future events in time series data.
That's the theory at least. I always get a little skeptical when people just throw neural networks at everything, though. Just because the data has a sequence doesn't mean that how it's represented is the same for language versus numerical data. I'm just saying, we should be critical here. It could be, and maybe it is, a case of overusing a tool that's just not the right fit.
That's a fair point. And I think this paper actually addresses that skepticism pretty well. They've done some extensive ablation studies, which is a great way to validate. And let's get into it, because the results are kind of surprising. What they found is that pre-trained LMs, large language models, do not significantly improve time series forecasting. In fact, in many cases, just removing the LM or replacing it with simpler attention mechanisms actually improves performance.
Whoa, okay, hold on. That's kind of crazy, isn't it? So all that massive compute, the billions of parameters in these huge LMs, is essentially doing nothing when it comes to predicting, say, stock prices or electricity consumption. It's not just a small difference, often better asterisk without asterisk without asterisk the language model.
That's what it seems like. And that's what I mean about the overfitting. They even found that shuffling the time series data, so removing the actual order of events, didn't drastically reduce the LM's performance, which to me suggests they aren't capturing anything meaningful about the temporal structure that these time series are about. If they don't care about time, are they even doing any actual forecasting or just noise?
Yeah, that shuffling experiment is really revealing. It suggests that the LMs aren't actually learning the sequential dependencies that you'd expect for effective time series forecasting. If you're trying to predict the next value in a series, shouldn't the order be critical? It seems like they're not tapping into that at all. And they also found LMs didn't help in few-shot settings, meaning having less training data, which you'd think is another area where pre-training would be beneficial. But not so much here, apparently.
Okay, this is forcing a rethink. I had a mental model where, given the success of LMs in NLP, their capacity for understanding context, applying that understanding to time series seemed like such a natural extension. I just assumed that capability would readily translate to other structured data. This is making me question my intuition.
Well, I've always suspected the magic of these language models doesn't necessarily come from their deep understanding of the world, but from their ability to, pick up patterns and regurgitate them with some clever tweaks. It's like a parrot that's learned the grammar but doesn't know what the words mean. So, when you throw out some numerical data, it's still picking up patterns, but it's not doing any meaningful reasoning. The sequential patterns in the time series data are fundamentally different from the structure of human language.
And the computational cost is insane, isn't it? They say that these simpler models, just using attention layers or simple transformers, they're orders of magnitude faster to train and use. So you're spending so much more energy and time for essentially the same results, or even worse. It does make you wonder what's the point of these complex systems in these situations?
Yeah, the energy implications alone are concerning. We're all pushing for more sustainable AI. And if you can achieve the same performance with far less compute, that's a huge win, not just for the environment, but also for the accessibility of this technology. This should make us consider these things more. It seems that LMs are not just computationally expensive, but also they do not leverage the sequence in time series.
Exactly. It brings to the forefront this trend where everyone is so eager to jump on the newest, shiniest deep learning technique that they ignore the basics. If a simple attention model, or even just a linear model with some clever preprocessing works just as well, we should ask, why are we overcomplicating things? I suspect if you just had a really solid mathematical model, you might even do better than that.
And they do go into some detail about what encoders work best for time series data, which is helpful. Turns out that just using patching, basically breaking down the series into smaller parts, and then using a single layer attention mechanism, they call it pattern, works surprisingly well. For smaller data sets, it's even competitive with the LM-based methods.
Okay, so the pre-processing and the attention layer are the key pieces, not the massive language model itself. So it's like preparing the input data in a way that a more focused neural network can understand it. This is great. It's like finding that you can achieve the same results as an advanced tool with a well-prepared input and a simple tool.
Yes, and to me, that's exciting. It highlights the importance of good old-fashioned feature engineering, something we've been kind of ignoring recently. We seem to have this just throw raw data at a neural net and hope for the best kind of approach. But these results point to the fact that the right kind of data representation is essential, even more so than the complexity of the algorithm itself.
Right. And it also calls into question a lot of the hype around language models as these universal problem solvers. It feels like we're still very much in the trial and error phase when it comes to figuring out where they're truly effective and where we need to look. For other tools, it's definitely not a one-size-fits-all solution.
I guess that's the ongoing lesson here, right? These tools are powerful, but they're not magical. They have their strengths and weaknesses, and it's crucial to understand that. If we are serious about building robust AI models, we need to look beyond simple pattern recognition. This study shows us how important good research with ablations is. We need to think about data representation and really understand the task at hand, not just blindly apply some hyped-up technique.
Exactly. It's not about being anti-LMs, it's about being scientific. I mean, LMs are fantastic at what they're designed for, language. But we need to be honest about their limitations and the fact that just because something works well in one domain doesn't mean it'll automatically work well everywhere else. We need to keep asking the why and how and keep experimenting with new ideas that better understand the data, instead of just sticking to the latest trend.
This whole discussion also brings up the idea of transfer learning, and when it actually works, and when it doesn't. So these LMs are pre-trained on massive datasets of text. But this study seems to show that that kind of knowledge doesn't transfer well at all to time series forecasting. The patterns are so fundamentally different that there's very little cross-benefit, and even seems detrimental due to the computational overhead.
That's such a crucial point. We often assume that learning general patterns in one domain should help in other related domains. But this paper points out that this type of transfer learning does not always translate well, and it might even come with unnecessary baggage. It's like learning to play a piano and expecting to excel at playing a guitar. They are related, but they require different skills and techniques.
It is a classic case of domain adaptation gone wrong. The representation that works well for human language isn't necessarily suitable for time series data, which has its own unique structure and temporal features. So it might just be the case that for time series, we're better off focusing on algorithms that have been specifically designed for time series analysis and not repurposing ones meant for text. It really highlights the need for specialized AI models for each type of problem.
And what I found interesting is the authors of the paper did mention that. They're not saying that LMs will never be useful for time series. They think they could be useful in multimodal applications where you have both text and time series data. So maybe you want to make predictions based on financial news and market data. In cases like this, they may bring some benefits.
Ah, yes. That makes complete sense. That's where the text understanding part of the LMs can actually add some value. Maybe analyzing news events for impact on time series data that might help you predict market fluctuations. In a multimodal setting, the LM's capabilities become much more relevant and useful. So, it's not that LMs are useless, they just need to be applied in the right context.
Right, and to me that feels like a much more sensible application of language models. It's about leveraging their strengths, not trying to force them into situations that they're not designed for. It's also interesting to consider in that kind of multimodal case. Would we need to pre-train them specifically for those sorts of problems? I guess the answer is also still up in the air.
Definitely. It's a call for more nuanced, more thoughtful application of these advanced technologies. We need to move past the one-size-fits-all approach and really dig down and understand what's going on with the data, and choosing our approach wisely. This paper is really highlighting that we need to get back to the core principles of data modeling.
Absolutely. It's about being more precise in our selection of the tool for the task. Language models are great at language, but they might not be the best solution to everything. I think that many researchers are drawn towards the newest and biggest models that they can use. I am guilty of that myself, I guess. But at the end of the day, efficiency and effectiveness must be our priority. We must not use tools because of their popularity, but because of their usefulness in specific use cases.
Yes, it's a lesson in humility for all of us, including myself. It's so tempting to fall into the hype, especially when we see exciting new tools like these language models. But good science demands that we look past the flash and the buzzwords and focus on good experimental design and clear understanding of what's working and why. To me, this is an important call to question the conventional approach and explore better alternatives.
This paper made me think about how often, in neuroscience and AI, we tend to look for single solutions for complex problems. But the brain is an orchestra, not a single instrument, and maybe our AI systems need to start thinking in a more modular way. Maybe combining different kinds of algorithms, different types of neural networks, could be the key to building more robust and adaptable systems. It's not about one architecture or one method winning, but about finding the right combination.
That's such a great analogy. It's so important that you're bringing this up. It's not always the case that the biggest or the newest model works the best. Thinking about modularity, it's about assembling the right components for the specific problem, instead of just trying to apply a single monolithic solution to everything. It emphasizes the importance of system design rather than individual model performance.
Right, and it also feels like we need a more open approach to how we design new algorithms. Maybe there are approaches that have been lying on the sidelines of AI development that could have a major impact in the future. We are kind of stuck on this idea that deep learning and neural nets are the only key to intelligence. And this paper sort of subtly points out that we shouldn't ignore all other tools. It could be time to explore alternative approaches that maybe better suit different types of data.
And maybe also we should take some cues from how the brain functions. It doesn't operate using just one algorithm, and it's extremely energy efficient. Maybe that combination is the key, the efficiency and the modularity.
I agree completely. Perhaps instead of building bigger models, we should be focusing on smarter architectures, incorporating insights from neuroscience about how the brain manages its resources and uses specialized modules for different tasks. That way, we might be able to move beyond general pattern matching and towards more genuine problem solving.
And maybe it means exploring different kinds of algorithms entirely. Algorithms that are less data hungry, that are more interpretable, that can learn from less data and better capture the fundamental structure of the data. We might be limiting ourselves by only focusing on a single framework.
Exactly. It's not to say we should just abandon LMs. They're still incredible tools. But we need a more nuanced understanding of where their strengths lie. And perhaps, more importantly, where their limitations are. It's about going past this hype and focusing on where they actually bring tangible improvements. And also considering the cost, both in terms of computing resources and understanding in interpretability.
This research brings up a question for me, which I'm hoping we can all think about. How can we, as a research community, avoid the trap of applying new techniques simply because they're trendy? What systems or protocols can we implement to make sure that the fundamentals like careful research and ablation studies are always prioritized? I mean, this research shows that those simple ablation methods can lead to some really counterintuitive results.
I think it needs to start with education. There's a huge focus on learning the newest neural net architecture, or the most advanced deep learning method, but not as much on learning fundamental research methods. I feel like many researchers forget that they are supposed to do research, not just build something that works. We need to encourage a culture of rigorous experimentation, of asking fundamental questions, not just chasing the latest fad.
I completely agree. It's not about the quick win, but about the long-term, foundational research that builds true understanding. And I think we as a research community have a responsibility to challenge these things when we see them. When we see an LM being used where it shouldn't be, and when we see corners being cut.
Yeah, this reminds me of a saying that I heard from somewhere: we don't know what we don't know, and that's what this research and our discussion here should be all about. We need to keep pushing the boundaries of understanding what works when and why, and we need to have the courage to challenge existing assumptions, even if they are popular.
It's about critical thinking. I feel like it's more important than ever. When we're dealing with increasingly complex systems, we cannot blindly apply a single method to every problem just because a famous company says it works. We have to be diligent, skeptical, and always ready to change our views. And to be fair, I will also take all of this with a grain of salt, as we should always.
Right. And I think that's a great note to end on. This paper is such a valuable lesson in that very critical thinking that you're talking about. And hopefully it encourages us and everyone to engage in more thorough and thoughtful research. I think it is important to move past just black box AI techniques and focus on getting a better understanding of the inner workings of AI, and also what are the best tools for specific tasks.
Indeed, and hopefully this also sparks a greater push towards sustainable and efficient AI, which is crucial for the future. And maybe it gives us a new perspective on what the future of AI might look like.
Yes, it's time we stop chasing simple solutions and start exploring the complexity of the problems themselves and find the right solutions for each task.
Well, that wraps up our discussion for today. Thanks everyone for joining us on this cognitive spirals journey.